Dr. Nardi here, back with another video, and in this video we will cover correlations and their importance. By the end of this presentation, you will understand what correlations are and how they work, know how to compute and interpret a simple correlation coefficient, and learn about other types of correlations and when they should be used. So what are correlations? A correlation examines the relationship between variables. It's represented by the letter R with a subscript xy, and its value can range from negative 1.00 to positive 1.00. Essentially, a correlation tells us how the value of one variable changes in relation to changes in another. The most common type of correlation is the bivariate correlation, which involves two variables. Specifically, the Pearson product moment correlation is used to examine the relationship between two continuous variables. There are two main directions a correlation can take. The first is a positive correlation, also called a direct correlation. This occurs when the variables change in the same direction. In other words, when one variable increases, the other variable also tends to increase. The second type is a negative correlation, or an indirect correlation. This happens when the variables change in opposite directions. So when one variable increases, the other variable tends to decrease. Here are a few key things to remember. First, as we mentioned, correlations range from negative 1.00 to positive 1.00. Second, and this is very important, the strength of the relationship is indicated by the absolute value of the number. A correlation of negative 0.70 is just as strong as a correlation of positive 0.70. It's often better to use the terms direct and indirect instead of positive and negative. This helps keep you from assigning a value judgment like saying one is good or bad. Finally, correlations are represented by the small letter r with a subscript to show which variables are being correlated, like r, x, y. This is the formula for computing the Pearson product moment correlation. It looks complex, but it's the mathematical engine that allows us to boil down the relationship between two variables into that single r value. A great way to visualize a correlation is with a scatter plot. By plotting the data points, the general shape of the collection can quickly tell you whether the correlation is direct, positive, or indirect, negative. Here in figure 5.1, you can see a simple scattergram with data points plotted on the x and y axis. On this slide, you can see what a perfect direct or positive correlation looks like. Notice how all the data points fall on a perfectly straight line, indicating a perfect one-to-one increase between the x and y variables. This slide shows a more realistic scenario, a strong but not perfect direct relationship. You can clearly see the upward trend, but there's some variability in the data points. They don't all fall on a single line. And here we see a strong but not perfect indirect relationship. The data points clearly trend downwards, showing that as the x variable increases, the y variable tends to decrease. When you have multiple variables, you can display all the bivariate correlations between them in a correlation matrix. This table shows the correlation between income, education, attitude, and vote. For example, the correlation between education and income is a direct correlation of 0.574. So how do you interpret the strength of a correlation? This table provides a helpful rule of thumb. A correlation between 0.5 and 1.0 is generally considered strong. A value around 0.3 is moderate, and a value from 0 to 0.1 is considered weak or non-existent. Going beyond the correlation coefficient itself, we have the coefficient of determination, or R squared. This is a very important concept. It tells us the percentage of variance in one variable that's accounted for or explained by the variance in the other variable. The stronger the correlation, the more variance you can explain. The flip side of this is the coefficient of non-determination, which is the amount of unexplained variance. It's also known as the coefficient of alienation and is calculated as 1 minus r squared. This chart provides a great visual for shared variance. If the correlation is 0, the coefficient of determination is 0, and there is no shared variance. If the correlation is 0.5, r squared is 0.25, meaning 25% of the variance is shared. And with a strong correlation of 0.9, r squared is 0.81, meaning 81% of the variance is shared between the variables. This brings us to the most critical point about correlation. Correlation does not equal causation. There is a positive correlation between ice cream consumption and crime rates. But does eating ice cream cause crime? Of course not. A third variable, in this case the outside temperature, is influencing both. Correlations only express an association, never causality. Software like SPSS makes it easy to compute correlations. This is the bivariate correlations dialog box, where you would select the variables you want to correlate, like income and education. And here is the resulting output. You can see the Pearson correlation between income and education is 0.574. The output also gives you the significance level and the sample size, or n, which is 20 in this case. You can also use SPSS to create scatterplots. This is the chart builder dialog box, where you would drag and drop the scatterplot option and assign your variables to the axes. This is the simple scatterplot generated by SPSS, which visually represents that 0.574 correlation between income and education that we saw in the output. While the Pearson correlation is for 2 interval level variables, there are many other types of correlations for different kinds of data. For example, if you are correlating 2 nominal variables, like voting preference and gender, you would use the phi coefficient. If you are correlating 2 ranked variables, you would use the Spearman rank coefficient. Sometimes you want to explore the relationship between 2 variables after controlling for the effect of a third variable. This is called a partial correlation. It allows you to remove the impact of a mediating or confounding variable to better understand the direct relationship you're interested in. This is the dialog box in SPSS for computing partial correlations. You can see that ice cream and crime rate are the variables of interest, and we are controlling for the outside temperature. Here is the completed analysis. After controlling for the outside temperature, we can see the new correlation value between ice cream sales and crime rate, giving us a clearer picture of their relationship without the confounding effect of the weather. So to summarize, the correlation coefficient is a useful descriptive statistic that shows how things are related or what they have in common. It's crucial to remember that this relationship is associative, but not necessarily causal. The correlation coefficient provides valuable information about how variables change in concert with one another. With this understanding of how variables relate, we can now move on to our next topics: reliability and validity, where we will learn how to determine what differences in outcomes truly represent. Please like, subscribe, and share this video. I will see you all in another video.